All right, so this is my final. I wish I could say final screencast, but unfortunately not. This is my final mind map, and put a bit of thought into this, and I tried to cover the whole breadth of semester and put into 10 dots. And obviously, we got to start with Maxwell. Maxwell's where we started everything. Every conversation we had dealt with Maxwell's equation. And then from Maxwell we derive the wave equation, and also really important to we get from Maxwell is the polarization. Polarization in a couple of the equations. I know Ampere's law and Gauss talks about polarization. That comes right from Maxwell, and that is a key concept here in this class. And I need to actually put another arrow in because I didn't forgot that I need to put. It is there. Never mind. But when we talk about transmittance and reflectance, I'll talk about a little bit more about that in a little bit. But that includes that. This is a big bubble, which includes things like Snell's law, which is all part of how much of something transmits and how much of it reflects. We need polarization because the way and what polarization is how lights wobble back and forth. It's the shaking of charges, and it's the way that those shaking charges interact is what is what can cause reflection, refraction, or at least refraction and reflection. I should also then add another arrow. Oh wow, I'm finding all these cool new arrows to put. How the charges shake out deals with interference patterns and diffraction, and all we're doing is we've got because the way the charges shake creates the electric fields, and the way the electric fields interact create little pockets, bubbles of light, or spheres of light that interact with one another. So that I think that really all comes from polarization, right there. And from polarization, and I really this was a bubble that I think I almost not put it in, but I did because polarization is just too big of an idea. Because we have S&P polarization, we have the role of like the Jones vectors, which talk about phase and phase shifts, and we have the actual polarizer, the physical apparatus, which I think for me has been easy to get those two confused. The polarized light versus the polarizer, the effect of the physical polarizer, the crystal that we put the light through, and we put something through what we could say interface, but that's not really appropriate. They're quite well. I guess it could be. So I'm gonna connect that because putting it through an interface can create a phase shift, and that's so key. Depending on what direction you are, vertical, horizontal, or somewhere in the middle, it depends how the light acts, which include things like circular polarization and all of that crazy stuff. So phase and phase shifts was a huge part of the semester. We did a couple labs that were based right on that key idea, which comes from polarization. So we got the wave equation. And then phase. By phase, I should probably clarify. E to the I, it's kr minus omega t, and that is so that exponent is the phase, and how that can change. So anyway, so all these good ideas. I wish I could have added, but I couldn't because I don't have enough bubbles. But things like wavelength and things like frequency, and anyway, that's all part of the wave equation. So I'm not going to go there with bubbles for those. Plane waves. And I think my biggest surprise over the semester was so much of the concepts that we talked about over the term, like image formation. I did not realize you could only have with rays, and how much of the semester we spent on plane waves, when really all the interesting things we do in general physics involve rays. And I know you pointed out many times throughout the semester that we're using a laser, and it just so happens that it follows the same laws of like Snell's law. So image in equals image or um, uh, angle in equals angle out, and they tend to transmit and reflect in the same ways, but it's really rays that's required, not plane waves. When we're really talking about things like image formation, that is those are rays, and I think that throughout the semester, even I think in one of the oral exams, one of the students even said that a plane wave is just a bunch of rays, and which we've learned is not true. But that distinction, I think, was probably the biggest surprise for me, or the biggest thing I learned over this semester was that. And I guess if we went in on the Econal, I never would have gotten that. So I take back what I said in my final. But it's already graded. So anyway, and key then, so then key to this idea of transmittance and reflectance is this interface. Interfaces take part both are involved both with rays and plane waves, and then interface. Similar thing for interference and diffraction, where you have two different rays or several rays that are interacting and causing each one to change just a little bit. That so those one example is the Huygens principle. We've got Fraunhofer and Fresnel, and they all talked about those series, and we got that, and then that is then we get to image formation. Those questions about how how far distance z do we can we be do we have, can we go before the image completely resolves or into itself or into itself because of the amount of diffraction that is occurring, and that is ultimately, I think, it's funny because image formation, when we think about optics, at least for me, that is so key. And yet, it didn't seem like it was until the end of the semester when we finally talked about how is it that we can see images and how do they form on a screen. And yet, I think that I think that that is just so much of a key component. But until you talk about rays and interference and diffraction and how does rays reflect, how do rays transmit and reflect, you can't get there. And so everything we did with plane waves can't get us to images, or at least as nicely. So that, for me, is what the semester was all about.